running.
Good afternoon. My name is Isabelle Guillon, and I'm one of the co-organizers, and I will share the session and the next session. So it's my great pleasure to introduce Richard Zemel, who will be the next speaker, and talk to us about few-shot learning in context. Richard is a student of Jeff Hinton at University of Toronto, where he still works. And this is a fake background of his real office. Richard's work on few-shot learning, and in particular prototypical networks, has had a considerable influence in a very short time. His paper from 2017 has already over 2,000 citations. And he's also co-authors a very influential paper on Siamese neural networks for one-shot image recognition. And so we are very glad that meta-learning has attracted his attention, because his interests are very broad, and it seems that no hard problems resist him. So Richard, we're very much looking forward to your talk.
Okay, thanks so much for the generous introduction, Isabel. Very nice. So I'm going to be talking, and I'm not sure if I'll be able to see what's happening in the chat. So if I welcome interruptions during the talk. So if you have a question or a comment, don't be afraid to speak up, because I'm not sure I'll be able to see it. Okay. And Isabel, I guess if you see something in the chat, then please do let me know. Okay. So let me get started. I'll share my screen and get going here. Hang on 1 second. Yeah, so sorry. Just 1 second. Let me figure out where the right screen is. Okay, very good. All right, so I'm going to be talking about few-shot learning in context. And to get started, I'm going to transport you to a different place. And it's a fond memory for me. One of my favorite places to travel when travel used to be possible was Southeast Asia. And I especially like fruit markets. And some of them look something like the one here shown in the center. And it's very fun to try to learn and identify new fruits all the time. So, you know, if you look over here on the left, I'm sure most people recognize the one in the middle as a mango. The one on the top may be a little bit harder. So that's a jackfruit. And down below here is a mangosteen. Okay. And then on the right, we have a famous one, the durian, which is the prickly one, and above is an Asian pear. All right, so a couple things I wanted to point out. First, the fact that it's a fruit market makes it easy to recognize something. So, for example, we can recognize that something is a durian and not like a hedgehog. That's and a second thing is that, like, this Asian pear up at the top is a little bit tricky. So recently I was at Toronto at a fruit market, and I mistakenly identified it as a yellow apple because I was out of context. I was not in an Asian fruit market, and I bought it thinking it was a yellow apple, and turned out it was an Asian pear, which wasn't so bad, but it was a surprise. So these examples bring out the idea that context is really important in learning about new things and being able to identify them accurately in the future. Most of the machine learning successes, the most notable ones, generally are in this independent, identically distributed setting, you know, made famous first foremost by ImageNet, where you have, you know, 1,000 classes and 1,000 labeled examples for each class, and the test set's drawn from the same distribution. But human learning, in fact, is very non-IID, right? So we're constantly learning new concepts and tasks. And the typical learning doesn't require fully labeled data. And also, back to the idea of context, we can readily identify relevant context. So if I'm wandering in the streets of Bangkok, I'll see a stand with colorful things, and there's a good chance it's a fruit market. And given that it's Bangkok, there's certain fruits that are going to be relevant, right? So I might find things like durians there where I won't find them in your standard North American fruit market. So this is the idea that you can return to an old context and rapidly recognize things even when you haven't been there for a long time. So this is kind of one of the many approaches that involve generalizing beyond the IID setting. And I think that's some of the most interesting work these days in machine learning is going beyond IID. So it goes under lots of different names. So examples include things like domain adaptation and generalization, data set or distribution shift. Okay, so these are just a few of the examples. And I think of few shot is one of the primary methods these days that people are studying this idea of going beyond IID. And because really what we want to do there is learn a new task or a new class with just a few examples, all right? And those, so those aren't drawn from the same distribution necessarily as the inputs, as the original training distribution, right? Because they are from new classes. So just by way of definition, the training is known as the support set, and the test is a query. So in this kind of the way the few-shot classification has been defined, right, is that we have this mini training set for these new classes called the support set, shown over here. Like we could have, two examples each of the three classes of the cats, the sheep, and the pigs. And then the query set you have to identify as one of the three. Right? And this famous paper by Brendan Lake and colleagues, support set was a single example here of a segue, and the query set were various things that had to be identified as a segue or not. All right. So here we have to apply the knowledge from this limited support set to the query set. So there's lots of limitations with this current paradigm, and it's fairly artificial. So one thing is that it's split up into episodes, which themselves are split up into support and query. And there's been some interesting work showing that, for example, there was some original work back in 2016 on matching nets done by Oriol Vignoles, who was the first speaker today, and colleagues. And they looked at the idea that you want to match what's happening at training and at test, right? So this is a notion that's common in machine learning, right? You want to optimize performance by matching your training and test distribution. And so since it was testing episodically, we should train episodically. Then there were some results that followed that showed that that's not necessarily the case. You can get excellent results by just doing pre-training, it's called, which is like training on big supervised nets back to the ImageNet idea, and then just doing the episodic test time, and can get performance that just about is on par with the episodic training. So that's a interesting question of whether this episodic thing is important, and more generally, how important is it to have this support into this split into support and query. I'll get back to that in a minute. There's also this notion of fixed support and query sizes. So that's something that the field has been addressing. So one notable example that deviates from that is a data set called metadata set by Lenny Triantafulu and colleagues. And that is where you have at test time, you have different support, numbers of support or shots per class, and different number of classes in various episodes. And turns out that makes a significant difference as to what methods are best. The other thing is that another artificial component of few-shot learning is that it's only testing new, not old classes, right? So you don't revisit old classes, and that's obviously something that doesn't really apply. If you think back to the fruit example, we aren't gonna only ever see new fruit, we're gonna see old fruit as well, all right? And furthermore, there's only labeled examples in the support set, right? And so typically in the real world, we'll have lots and lots of unlabeled examples. So I've done with my group various papers looking at these questions. We've had work on semi-supervised few-shot learning, on kind of what we call incremental learning, which is learning with old plus new, mixing those up. There's a lot of work in the field on that, trying to avoid catastrophic forgetting and be able to learn new things efficiently. What I want to focus on today is a different vein of work, and that's about trying to develop a more natural, continual few-shot learning paradigm. For this, I want to just bring up the idea of context, and so a dictionary definition of context. It would be the circumstances that form the setting for an event, statement, or idea, in terms of which it can be fully understood and assessed. We're going to look at two kinds of context. One is spatial and the other is temporal. So spatial, you can think of it as what's the stuff that's around the item that's going to be recognized, right? So what are all the other things on the fruit stand? And temporal could be events or things that happen at a similar time. So that's the kind of temporal continuity idea that, again, if I'm in Bangkok and I'm traveling the streets, then that gives me some idea of what the context is and what to expect next. Right? Okay, so the paper I'm going to start off with is some new work that's available on arXiv. It's also in the ICLR upcoming ICLR conference called Wandering Within a World, Online Contextualized Few-Shot Learning. And this is work with my colleagues, Mangi Ren, Michael Islanu, and Mike Moser. So to start with, the aim is to have more of an online natural learning experience, right? To get rid of this kind of artificial episodic setup. And so to do this, we came into the trend, wanted to develop a more realistic learning environment. And so we took something called the Matterport 3D environment that contains about 90 indoor worlds with panoramic imagery, and use this to simulate the idea of moving through the world, okay? So in some continuous way. So getting away from the notion of there being these kind of IID things. Instead, we have this continuous setting and fairly realistic, in this simulated world, as realistic as we could get in this kind of simulator. And what we're trying to do in this, we developed a data set we call the roaming rooms data set, and this meant to be simulating wandering through a house. So this is a kind of natural environment. You walk through a house, sometimes you enter a new room. You can also revisit old rooms. You're gonna see, when you come into a room, you'll see some objects that were there before and other things that either weren't there or you might not have noticed in the past. And then we're gonna evaluate it at each time step. So the idea is there's gonna be a little bounding box surrounding the object of interest, and the system has to respond with classifying that object and with the label for that object. And there's no kind of episodic idea here. There's just this continual thing where you get to see an object and recognize it as, as one of the known objects. It can also be a new object, in which case you have to say it's a new object. Okay, so that's the basic setup here. And I'm going to play you a little video just to show you how we accumulate training instances through time, all right, in this setup. So you can see you kind of in a room, and the system is going to fixate on different objects. Each one of those is an instance that's presented to the system. It's an input to the system, and it has to identify it. And in this case, we have white and red objects. The white ones were the ones that were labeled, and the red ones that were unlabeled. So we wanted to get at the idea that it's a semi-supervised setting. Sometimes labels aren't available, okay? And there's different rooms. I don't know, it's too fast to see that there, but there's the kitchen, there's kitchens, there's living rooms, there's family rooms, each with their own kind of natural objects that happen to appear there. And also you'll see the same object from different viewpoints, okay? So that's the idea that you're now recognizing. In this case, it's object instances, not object classes. You're gonna see the same object from different viewpoints, depending on where the camera is in the room and where it's, how it's looking at the object, okay? So that's the basic setup of our simulator. And so now let me tell you some of its features. We call it online contextualized few-shot learning. And so here you can think of the model has to predict known classes based on just a few examples, and also new classes in a sequence. So I'm going to run through kind of like a simulated sequence here. There's a world and an agent. Let's say the agent is wandering in the kitchen. So the agent is not, just to be clear, this agent doesn't have control. It's actually just going to be, it's not deciding where to go next. We're moving the camera and taking the pictures, but it's simulating the idea that the agent's wandering in the kitchen. And let's say it encounters a cup. So the world, looks at a cup, and the agent now is supposed to, which is the system, hasn't seen this before. So it's supposed to say this is a new object, all right? So we'll call that class 1. At the next step, it looks at a saucer, or let's call it a plate, and it's going to be new as well, all right? It's going to be class 2. And now it looks back and sees the cup again, and it has to recognize, and it should call it class 1, but it makes a mistake and says that it's new. Okay, and then it could see the plate again. It correctly classifies it as class 2. So the process here is online and incremental. It's kind of continually getting new classes. It's also being tested on old classes. And as well, it has to predict when something is unknown. Right? And there's no real separation between what's support and what is query. Right? Every example is used for evaluation. So that's the basic setup. The framework also allows for semi-supervised learning. So that's this dashed line around the classes. So that means that the system doesn't actually get labels in those cases. So it doesn't, when it's learning these things, it has to learn in the face of unlabeled data. So it's making use of the unlabeled data. Okay, so it doesn't actually get a label after making these predictions, right? So it turns out the sequence we see actually belongs to a scene in the kitchen, and the classes that occur are correlated because they all belong in the kitchen. Okay, then it can go back to other rooms. So, so for example, here, I'll show you. So it starts off in the kitchen, that's the context. Then it can switch and come out of that room and go into the office. So that's another environment or context, all right? It goes to the office and then goes to the living room and can come back to the office. So it has this characteristic of, you know, seeing new things all the time, but also returning to old and making sure that it doesn't forget the old, okay? So it's has that flavor of, that characteristics of online learning, okay? One important note here is that this context ID isn't revealed to the model. So it doesn't know what room it's in or anything. It has to be inferred, okay? So again, it's trying to get by with little, as you know, as sparse in terms of labels as possible, okay? Inferring the context is beneficial because based on the context, you know, there's certain kinds of classes that are relevant in each context, right? So more generally, there's some challenges in online learning that are brought up by this setup. One is, as I mentioned, it has to retain or at least rapidly recover old contexts. And there's various ways of achieving that. One is to store old data. So this is common in kind of continual or online learning, is to have a replay buffer of past examples. And there's various ways of trying to make that efficient, but that's one way that people have handled this question of remembering the old, not forgetting it. You can store old memories in the weights. So the weights represent knowledge about past classes. And so the weights can be stored and there can be a penalty, some sort of penalty like a regularizer, not to change the weights too much, to forget the old. And then there's some more explicit memory models. And that's the approach that we took, and I'll describe that in a minute. And the aim in general is to try to learn new contexts and classes without too much capacity and computational overhead, right? So you don't want to think about the network as adding a whole bunch of hardware every time it has to learn a new fast. So the idea is to reuse existing hardware, existing setups to be able to expand and recognize new classes all the time. And the interesting question is how to capitalize on the task relatedness. So we have new classes that we're learning about that share some similarity with old classes. So can you, by learning about the new classes, can you kind of help forward transfer, that is learn about other things that might appear in the future, as well as backward transfer, like by learning about the new one, not only do you not want to forget the old kinds of classes, but you may want to actually get some improvement by seeing something else that is related. So that's called backward transfer. So these are the challenges in online learning. So now let me tell you about our approach that we took in for this particular data set and the setup. We call it the contextual prototypical memory. And it builds on the idea of a prototypical memory and the contextual RNN. So it has two main components, this RNN on the left and a memory on the right. The temporal context is captured by the RNN. So there's a CNN that processes the images. RNN is remembering something about the temporal context, the kind of, you know, how things like context change slowly over time, right? So it's in one room for a while. And then but again, the environments or rooms are implicit, so there's no signal for when it does change. And then in terms of the memory, how the classes are stored, we're going to use the simple idea from the prototypical network model that was mentioned earlier, where you just have a single prototype in the embedding space to represent each class. right? And a new class is, when a new class is defined, the system decides it's a new class, it adds a new prototype, and there's a kind of online averaging approach that's illustrated by these equations that basically just gets at the idea that when something else is a new instance of an existing class, then that gets incorporated into that class, the prototype gets updated. And so that enables some sort of hopefully forward and backward transfer, right? So there's the embedding model that should update to do a good job on other classes, as well as when it recognizes an instance of that class, it should improve further recognition of examples from that given class, right? The semi-supervised part of it that I mentioned complicates things considerably. So you have to update the prototypes, in some cases create new ones without the benefit of the labels. All right, so that's a challenging problem. And let me tell you about two interesting properties that I want to highlight about the model, two ways that the RNN interacts with the memory. Okay, so that's what's illustrated here with this little context vector and control parameter. So I'll tell you a little bit about the details of that. So there's a kind of residual connection between the RNN and the CNN, okay? And that, so that can kind of bias the thing with the temporal context, right? So you can think of it as a way of learning some memory organization. So subjects in the same temporal context can be grouped together. So here's an illustration of how that's possible, a kind of conceptual diagram. We have different prototypes in the prototype memory being stored of, you know, armchairs here and office chairs. The color is representing which context it's in, right? So what room it's in. Kitchen is blue, office is red, and the living room is green. All right. So since the visual features are similar, an office chair and an armchair might be nearby each other in the prototype memory. But now the temporal context acts as a kind of bias, so that there's an organization to the prototype memory. The things that tend to be that are in the kitchen will tend to be in the same part of the prototype memory space. And that comes from this residual connection. So there's a kind of common living room vector in the object classes, and this is very useful in organizing the memory and manipulating the kind of latent vectors. So this is an example of how the context influences the memory organization. And we did some visualizations, and we saw that this organization was in fact what was learned. This makes the memory more efficient when it returns to an old room. A second thing I wanted to highlight was how an interaction between the RNN and the memory are in terms of how to handle novel unlabeled examples. And this controls the reading and writing to the memory. So there's a separate set of parameters. So this is the probability of something being unknown, which is a key question, right? So if something's unknown, a new class has to be added to the model, a new class to the memory. And that has some control parameters, there's betas and gammas, and those are going to be learned by the system. And there's going to be a different one for reading and writing. Okay, so the idea is that if it's reading, it may be more less conservative. If it writes, it wants to be more conservative. It doesn't want to, you know, falsely write in too many objects. So this goes back to what I was saying before about the semi-supervised learning aspects complicates things. So it's difficult to know when a new thing should be created. So these parameters are learned in a way that makes it conservative with respect to writing the prototypes, right? So that's what I was saying. It's more conservative, assigning unlabeled examples to the prototypes. So there's some interesting parallels between the system as I describe it to the human brain. There's something that's been around for a while called the complementary learning system. And that has outlines some different functionality of kind of long-term statistical learning together with a hippocampal memory system. And the hippocampus is for storing and recalling novel concepts. And the memories then are divided into kind of working, episodic, and semantic memory. And so in our model, those can be identified with the contextual RNN as a kind of working memory. The CNN that's pulling out, you know, the kind of features from the data, that's more the kind of long-term statistical learning. And then we have the semantic memory that's being represented by the prototypes over here, right? There's some newer ideas in CogSci, something called contextual binding theory that shows that the kind of long-term encoding of information depends on binding spatial temporal context without forgetting it, all right? Without the spatial temporal context, things are forgotten. right? So there's some parallels to what we're doing here. The spatial temporal context has an important role in organizing the memory and remembering things. Okay, pause for a second, take a drink. As I said, if anybody has any questions, feel free to speak up. So I'm not going to spend too long on results, just the accuracy. We do some comparisons to other online methods, some online meta-learning, some other memory-based models, as well as an online version of prototypical networks. And then there's an offline system, which is interesting. So rather than worrying about things online, you can also test and say, well, let's imagine you saw all the data. How well did you do? So this is a kind of oracle or upper bound that you get here with this red dotted line in terms of the accuracy over time. The reason why these curves are going down, just so it's clear, is that over time we're seeing more and more classes. So the classification problem, is getting the n is getting higher and higher. So it's a harder and harder problem, and so accuracy is going to decrease over time. Okay, but the CPM model does quite well, sometimes approaching the oracle. Okay, so let me switch gears, and I'm going to talk about a second question about second direction that I think context is important. So maybe before I do that, just pause for a second and see if anybody has any questions or comments so far.
Yes, I might have a quick question.
Sure.
How do you control, oh, sorry, let me also quickly put on the video. How do you control the agent and determine that, that the agent somehow encounters in the environment all the complicated classes and not somehow roams around simple in the environment?
Right. So that's a good question. So we've, I presented it as if there really is an agent, but what we've really done is created a data set, which is going into the rooms and finding what we think are the salient objects and focusing on them. So the method by which the objects were found were, they had to be kind of large enough to be distinguishable and kind of present from different viewpoints, so it might appear more than once. So the idea was that it could appear several times. And so that was the criteria for deciding when we'd have see the objects again. So that was a creation of the data set. That was how we went about doing that.
Thank you.
Sure. Okay. Any other questions for now?
Well, perhaps could you comment a little bit more on the figures and explain, the relative advantages of the methods and what we really see in these figures?
Sure. I mean, these results. Yeah. So I think so the yellow is a kind of online meta learning that doesn't do a very good job in terms of being able to learn new objects. So one thing I should point out is that most of the online, this is quite different than standard kind of online or continual learning that people have looked at, which is one thing that's different is that we're going back and revisiting things. So that's a lot of the systems aren't doing that. Typically it's about always seeing new classes and new things and not testing old ones. So that's one thing that makes it more complicated. So a lot of the ones that we tried to get baselines for just didn't do well. We had to adapt them to be able to do that. We also had to adapt them to be able to do well on this additional problem of, deciding whether something is new or old, right? So this idea that we see something that's new and, is it, or see an object. And first you have to decide is it an old object or a new object. If it's an old one, you have to classify it as one of the existing ones, otherwise create a new class. So that's typically not dealt with in a lot of the continual learning things where, like I said, it's done more like, this kind of continual MNIST ideas. First you're going to see zeros and ones, then you see twos and threes, then you see fours and fives, right? So you're getting new classes all the time. So it's continual, but you always know that it's a new class and you aren't going back to old ones. So,
and in this case, for the online meta learning, there's nothing special that's been done for semi-supervised. So the unlabeled examples are not used at all.
Well, so we tried to adapt these things to use the semi-supervised to make realistic comparisons. So right, the left is supervised and the right is semi-supervised. You see here, but being able to cope with semi-supervised is difficult, especially for this thing as I mentioned, right? When you're having new classes, it's very hard to know that new class is potentially unlabeled, and the system has to decide whether it's a new class or not. It's when it creates to create a new class, and so that's a real challenge. And So things like online protonets, we adapted it to be able to do that, to kind of have this online flavor I was talking about. So it's a lot like the online protonet I showed as part of our model, but that doesn't have the RNN that has the spatial context. So that's one thing the contrast you can see between the green and the blue, for example. That's our CPM versus online protonets. The green one has the RNN, and so that gives it some temporal context that's important for recognition. So that gap's what you see from that kind of temporal context. We also experimented a lot with different kinds of memory models, and like the DNC is another one. So various kinds of differential neural computers, various kinds of memory models. We thought they would be great for this context, and despite Munge's, the student who really is a superstar, worked on all kinds of different memory models, tried to get them to work, and could never get them to outperform the simple protonets. So that was maybe future work. Other people will try to figure out how to get the memory models to work better.
So here you fix the number of entries that are given. And what is the proportion of labeled with or unlabeled with respect to unlabeled?
Yes, that's a good question. It's an evolving thing. So like over the course of an episode, we'll see some labeled, and then some unlabeled, and then some unlabeled. I think overall, I'd have to go back and check, but roughly, I think it was fairly balanced between labeled and unlabeled.
So a corollary to that, is that if you fix the number of labeled examples, do unlabeled data help?
Yes. So when we compare just doing the labeled, it's a little, these experiments are quite hard to test because it's not like you have these fixed test sets, right? So it's this continual thing, and so you're looking at performance over time. But we did an experiment that looked at that question that you're asking, which is to say, can you take an episode that has purely labeled versions and then insert some unlabeled ones and see if you get better performance on the labeled examples, right? Or on the examples. And so it's quite tricky to run that experiment, but we did show advantages to the unlabeled for sure.
Thank you.
Sure.
May I ask?
Yes.
What's the difference with continual learning and so you kind of create a hierarchy of concept, let's say, but you can also think of continually expanding the number of classes, which of course may be very critical for the performance, at least, because the classes are gonna explode. So yeah, these are the two questions.
So I'm not sure if I quite got the question. So we are continually adding new classes here. Those classes don't have any inherent hierarchy in a sense. So we don't assume any class structure. And in fact, we don't really know any class structure. The only structure to the classes is that, certain objects appear in certain rooms. So it's more of the contextual structure, but I don't think there's any hierarchical structure. I'm not sure. So maybe rephrase your question or tell me what you meant by the hierarchical aspect of it.
No. The fact that the context creates a hierarchy, and maybe not hard, but logical.
Mm-hmm. Yeah, so it certainly is a grouping of things, or it creates this additional structure in the context. But even the context is a little bit hard to define, right? Because we think of it as a context of rooms, but all that is implicit. The system doesn't actually know about rooms, and so it's just that certain objects tend to co-occur together. And if the system, there's a spatial context which is just from one presentation to the next. So if the system goes one room to the other, there will be a continuity between rooms as well. So it's not a very well-defined grouping, but there's a rough idea of things that are continuous in time. And then the spatial context is, some structure of just the visual appearance of the object and what's surrounding it. So all of those things are influence the learning, and I think are super important for the learning system to capitalize on those to do a better job. Like that's what the results show here. Like I was showing the difference between the RNN and the non-RNN based protonets is because of taking advantage of that spatial context.
Thank you.
Okay. Okay. So if there are any questions, let me transition to a second project that looks at a different kind of context. Okay, so and this is looking at, so the question is, what makes a class? So few-shot classification generally is defined based on semantic classes, like the example I showed earlier. You got pigs and sheep and cats. Okay, but classes are often defined based on other things, like, what's the appearance of an object, what kind of material is it, how is it could be used, what are the affordances. So these ideas have been around for a long time. So for example, if your aim is to sit, a rock can look very similar to a chair, but if your aim is to hit, then it looks more like an axe, right? Or a club. So the idea of a class can be fairly flexible and contextual. So this work we call flexible few-shot learning of contextual similarity. And it's inspired by some work in cognitive science by Amos Tversky. It wrote a paper called Features of Similarity. And so this is one of the studies in that paper. Subjects were asked to find the face that's of the three below that is most similar to the face above. Okay, so in the first case, people tend to choose this first face over here. Okay, and in the second case, it's the same test up above, and the two ones of the triple at the bottom or the end. The one in the middle is different. You'll see that the facial expression is different. And people tend to group, the one on the left tend to group the query face with the one on the left. In the example on the right, the query face was grouped with the one on the right. And so the notion here is that there's a grouping operation that the subjects tend to be doing, where of the three queries, two of them that are similar are grouped together, and then the query one is matched to the remainder. Okay, and that's what happens over here on the right as well. The two on the left are grouped, and so the query is matched to the remaining example on the right. So similarity here is very contextual. So what's the similarity of the query object to other ones depends on what other objects co-occur with the one on the bottom, right? So we wanted to get at the same idea, which is, the notion is that people are very flexible in how they define what's similar, how to group things together. And so we wanted to look at this in a few-shot learning setup. And so we have these flexible criteria that can appear during episodes, and we get new criteria at test time. So these are not actual examples from our data set, but just illustrations. So we can have, so each episode, there's a context that's involved. So the context could be, so you have one positive class that's defined, and then the query is, each example you have to say, does it belong to that positive class or not? So the episode one, the context is a living thing. All right, so the positive class is the elephants and the dogs. Negatives are chairs and pots. In the second episode, a new context, it has a handle. And so the pot and the cup are positive, and the table and the cat are negative examples. All right, so classes are being defined here flexibly depending on the episode context. And again, just as we had context in the other one, the context is implicit. It has to be inferred by the system. It's not told what it is. All the system's told is that the positive class are the two examples on the left, and the negative examples on the right don't belong to that class, right? And at test time, the system gets a new episode where the positive class is this elephant and teapot, and it has to, and these are negative examples. And now those are the kind of support examples for the class. These are the positive on the left, the negative on the right. And then the query has to be either said, is it in class, one of these positives, or not? Okay. It turns out the underlying implicit context here is color. In the second test episode, the context is it has four legs. So the elephant and the table are positive, and the teapot and the TV or monitor are negative. So one thing that's interesting is that the same object.
I apologize, Richard, but can you explain again what the system needs to give as answer? What is it expected to answer in when it gets test time?
Sure, when it gets I didn't show any queries here, but when it gets a query for this episode one, it'll get a query of something else that's colored, let's say, black, and so that has to say negative for the first episode. okay? Because it's not the color of the positive class, which is this kind of greenish blue stuff, okay?
So it's not asked on which basis it's making the decision.
Right. That's right. It just has to say, is it positive or negative? It's a binary classification problem for the queries. Is it in class or out of class? So episode 2, anything that has 4 legs should be positive. Anything that doesn't have 4 legs would be negative. So that's the correct answer for the queries for episode 2. Okay. And the system gets trained up on this just with positive and negative class labels.
This does have a reminiscence to psychology tests, you know.
Yes, that's right. That's right. Yeah. So yeah, as I said, we were inspired by it, but I also think it has some interesting practical uses. Not just so it is interesting, I think, understanding how we think of context. But I think practical uses, you can think of a context. So one example that comes to mind is, think of now a context is somebody doing a visual search or like a dating app. Okay, so in a dating app, somebody sits down and they, kind of online, they say positive, positive, negative, negative, positive, positive, negative, negative. Okay, so they're kind of saying what they consider to be a positive class and what they consider to be a negative class. And so the system has to quickly adapt and say, okay, what are the kinds, here's a new example is this, the system wants to recommend or show items that they think are part of the positive class. Okay, so that's kind of a practical example of how this, the context in that case is kind of personal taste and what that person is considering positive or negative. Okay, so it is like a psychology test, but I think it also has practical implications. So we've defined some benchmarks for this, which are image data sets that tend to have attribute annotations. So like we have this, the well-known celeb A data set, and we have positive examples. So one context would be male and smiling. So we'll take 2 attributes and call those defining the positive class. The negative examples are all things that don't fit within those 2, okay? Positive class here is cheekbones and earrings. Negative classes are the ones down below. So that's we have a whole bunch of training and test thing. We also did this with shoes. So we had to find data sets that have attributes so that we could easily define positive and negative examples. So, women in lace up is, these are the positive examples, these are the negatives, and slippers and slip-on positives and negatives, okay? So again, the system gets trained on a bunch of these and it gets tested on wholly new contexts. And the interesting thing that we added to make it more difficult is that the attributes at test time are completely novel. So it never, slippers and slip-on, if this is a test episode, will never have been part of the context during training. So it's really testing, again, it's like generalizing to new classes and furthermore generalizing to new attributes that weren't relevant at training time. They were part of the training set. It could have been that it saw one of these shoes even as one of the positive classes, like it did here, a very similar one. But the criteria that made it a positive will be different than what makes it a positive in the test time. Okay. And one thing that, so I mentioned early on that pre-training approaches often are very useful for this type of thing. You can run a pre-trained system like ImageNet and then run it at test time. And it does quite well on a lot of the few-shot learning benchmarks. Turns out that in this case, they don't work well at all. And I think it's partly because of this new attribute idea, okay? So I'll kind of skip through that. I'm noticing that we're in time. And the best results that we got were an interesting setup where we did unsupervised representation learning using a kind of contrastive learning. And that's our UFT, we call it, unsupervised representation learning, with some fine tuning on the task. Okay, and that did almost as well as a kind of oracle over here. The oracle does better on the celeb A and on the shoes. It's almost as well. The red is our best version of that. And similar models that are based on other things like standard proto-nets or standard methods of pre-training on the attributes don't do nearly as well. Okay. So I think I'll skip the visualization. It's kind of fun to see how it does. It actually looks at the right attributes to do the classification. So let me finish up with a couple open questions. One thing is that I've showed you different ways that context can be brought into few-shot tasks, both in terms of spatial, temporal, environment, what are the attributes that are relevant to something that you're looking at. And a lot of this says, well, maybe we want to rethink the kind of learning architectures and objectives that we train with. And I think, back to the online setting, like how can we integrate and coordinate short-term and long-term learning is really important. So one thing I didn't say was that one one aspect that's not ideal in the system that I talked about is that we actually froze our CNN at the bottom that was pulling out the features. And so that what learning of those features wasn't something that happened that happened on a pre-training phase. And the rest of it, the RNN and the prototypical network is what's adjusted. So we'd ideally like to, integrate both the short-term and the long-term learning. That's an open question. I think that's hard. And then there's an interesting question of a role for an active memory. So things like a prototypical network, or even the kind of differential neural computers, a lot of those memories, they're still kind of forms of storing memories. Whereas I think, so some recent work in cognitive science has shown that, and in neuroscience has shown that more of a generative model is important. So it could be like something like the hippocampus isn't important just in kind of recalling previous things, but in regenerating previous memories. And so I think that's a interesting question to end up with, which is how can we think of a more generative form of memory being useful in this setting? So I'll end there. Thank you.
I guess I need to